The universe is not only expanding, it's accelerating its expansion. And this has devastating consequences. The observable universe might be a bubble of 46 billion light years in radius, but even if we could travel at the speed of light, we could never reach that horizon. Not even in 46 billion years. Not even if we had an infinite amount of time. The accelerated expansion of the universe is keeping us away from the horizon. And this accelerated expansion is due to the mysterious force of dark energy. The pullback of dark energy is so strong that the furthest we could ever reach is 16 billion light years. We are only able to explore roughly a third of the visible universe, and also only if we had an infinite amount of time and could travel at the speed of light. This is so frustrating, isn't it? That's how much dark energy keeps us in our place. It prohibits us to explore the universe. But we don't want to question the ethical motives of dark energy in this video. We want to calculate the furthest distance we could ever travel, in a simple way. Let's start with Einstein, because you cannot talk about the universe without mentioning that guy and his theory of relativity. And the heart of this theory is the so-called metric, which is just a fancy word for distance. But instead of distances in space, we're talking about distances in space-time. In a flat space-time, we would have a Minkowski metric. And if space-time is curved, then the metric changes, and therefore the distance between events in space-time is also different. But according to current research in cosmology, the universe is most probably flat, globally. Of course, there are patches where black holes or stars or galaxies are curving space-time. But overall, the universe seems to be rather flat, so we can apply a Minkowski metric for the whole universe. But there is one problem. The Minkowski metric gives us the distance between two events in a static, non-changing spacetime. But the universe is expanding, as we know from Hubble's observation almost 100 years ago. So we have to include this expansion of space somehow in this metric. And in cosmology, the expansion of the universe, or to be more specific, the expansion of space, is characterized by the so-called scale factor. Put two galaxies into space, where space is a grid. The distance between the galaxies is 2 grid points. Space, aka the grid, is expanding now over time. The grid distance is still 2 grid points after a certain amount of time, but the real physical distance between the galaxies has increased by some time-dependent scale factor A of t. The scale factor tells us by how much the real physical distance has changed between the galaxies. So let's go back to the metric for our universe. The Minkowski metric would only give us the grid distance between points in spacetime, but we want the real distance, so we multiply the dr squared by the scale factor squared. And this is our final metric for an expanding flat universe. Now, how does this metric help us with our mission? Remember, in the beginning I said that even at the speed of light we could not reach beyond a distance of 16 billion light years. So let's assume we could fly with the speed of light. Another consequence of Einstein's theory of relativity is that light does not experience time nor space. It never covers any distance. It never experiences time passing by. And the same is valid for anything that moves exactly at the speed of light. So we can set the whole metric to 0. Then we rewrite the equation such that dr is on the left side and c dt over a of t is on the right side. All we have to do now is integrate. And on the left side, from 0 to r0, which will give us the covered coordinate distance, so the grid distance between 2 points. And on the right side, we integrate from t0, which is the time today, up to infinity, because we want to know how much distance we can cover with an infinite amount of time. But this is only the coordinate grid distance, so we have to multiply it by the scale factor at today's time t0. Looks quite similar to the integral from the thumbnail now, doesn't it? All we need to know now is find an expression for the scale factor. And we can find an expression for the scale factor by solving the Friedmann equation. From the theory of relativity, we know that space and time are influenced by mass. And from Einstein's famous formula, we know that mass is equivalent to energy. So in the end, it is energy which is influencing space-time and therefore influencing the scale factor. To determine how exactly energy is influencing the scale factor, we have to solve the Friedmann equation. In 1922, the Soviet physicist Alexander Friedmann used the Einstein field equations of general relativity to describe an expanding universe. And he had that idea before Edwin Hubble discovered the expansion of space. That happened 7 years later, in the year 1929. As a matter of fact, in the year 1922, most scientists thought that the Milky Way is still all there is in the universe. Oh boy, how our worldview has changed in the last 100 years. But back to the Friedmann equation. The Friedmann equation is a first-order differential equation and can be solved by separating variables, so no worries about impossible-to-solve differential equations. On the left side, we have the time derivative of the scale factor squared divided by the scale factor squared itself. This describes how the scale factor changes with time. This fraction is equal to the time-dependent Hubble constant squared. You can check this by comparing units. The unit of the Hubble constant is kilometers per second per megaparsec, so that's velocity over distance. A dot has a unit of meters per second, and A has a unit of meters, so we have velocity divided by distance, which is the same for the Hubble constant. So plugging in the current day for the time t, which is t0, we would get a value h0 of roughly 70 kilometers per second per megaparsec. This is the value that we're measuring today for the Hubble constant. That's how fast galaxies are moving away from us today. But they have not always moved at that speed, and they also will not keep on moving with that velocity forever. Now let's have a look at the right side of the equation. Here we have the entire energy density of the universe. In a simplified way, we're only dealing with radiation, matter, and dark energy, where dark energy is a constant density characterized by the infamous cosmological constant. More precise models include neutrinos, the curvature energy, and sometimes a differentiation between normal baryonic matter and dark matter. But for our case, those three densities are enough. Actually, we're going to reduce them to 1, because we want to find the easiest form of the Friedmann equation that is possible. So let's have a closer look at those densities. Notice that radiation and matter density are both time-dependent, but dark energy is not. Putting the time-dependent densities together with dark energy into a graph, we can tell that there must have been 3 phases in the history of the universe. First, the radiation density was much higher than both matter and dark energy density. This was the case for the first 47,000 years after the Big Bang. Then, matter took over and dominated the universe for about 10 billion years. But 4 billion years ago, dark energy started to dominate the expansion of our universe. Let's ask ourselves again, how does that help us with our mission? Well, we want to know what the furthest distance is we could ever travel, so starting now and going into the future. And for that, we need to know the scale factor. And the scale factor is influenced by the energy density in the universe. We can assume that dark energy will remain the dominating force in the universe and will even grow in its power in the future, since it is already higher than the density of radiation and matter. Therefore, the influence of radiation and matter will decrease drastically over time. We can therefore easily set the radiation and matter density to 0 for our calculation. This simplifies the Friedmann equation a lot. All we have is a constant density on the right side. So let's solve this equation. So this is the equation we want to solve. let's put the a squared from the left side to the right side first. Now we can write the a dot as dA over dt and take the square roots on both sides of the equation. So dA over dt is equal to the square root of the cosmological constant times the speed of light squared divided by 3 and the whole square root multiplied by a. As I mentioned some moments ago, we can solve this equation with separation of variables. So we put the a on the left side together with the dA and the dt on the right side together with the constant square root term. And now all we have to do is integrate on both sides. Integrating on both sides is pretty easy. The left side will give us the natural log of the modulus of the scale factor, but the scale factor is always positive, so we can just drop the modulus and have the log, the natural log of the scale factor. And on the right side, the integral just gives us the constant square root term times the time t. In order to get an expression for the scale factor, we just have to put both sides of the equation into an exponential function. And this is it, the scale factor for a dark energy dominated universe, and we can easily tell that the scale factor will grow exponentially with time, meaning that the expansion of the universe is actually accelerating. But let's simplify this expression for the scale factor a bit more. We need to remember the simplified Friedmann equation again. Here we see that the time-dependent Hubble constant is equal to the constant dark energy term on the right-hand side. But this constant term is not time-dependent, so the Hubble constant today, h0, must also equal that constant term on the right side. Now we can just plug in our scale factor into the formula for the event horizon of the universe, which is the farthest distance we will ever be able to travel, if we were able to travel at the speed of light. And instead of the square root term, we just have the known Hubble constant of today in the exponential function. All we need to do now is solve that integral. Since we're dealing with an improper integral, we will introduce the parameter lambda for the upper limit of the integral. Then we just integrate elementary, and in the end take the limit for lambda going to infinity. The exponential term containing the lambda goes to 0, and we're only left with c over h0 eventually. The speed of light divided by the Hubble constant today gives us the event horizon of the universe and the farthest distance that we could ever travel. Plugging in the numbers, we get 4,285 megaparsec for the event horizon, which equals roughly 14 billion light years. Finished. This is it. This is the event horizon of the universe, 14 billion light years. But wait. In the beginning, we said that the event horizon is at 16 billion light years, so why the deviation? Well, you probably know this graph. It shows that about 30% of the energy in the universe comes from dark matter and 70% from dark energy. But we have assumed that 100% comes from dark energy alone. Therefore, we neglected the matter part completely. Matter, with its gravitational pull, will slow down the accelerated expansion of the universe and therefore make the event horizon larger. If we were to live in a purely dark energy dominated universe, we could only travel about 14 billion light years. Thanks to matter, this distance is increased by another 2 light years. So, this is it. You're done. You have successfully calculated the event horizon of the universe. And if you enjoyed this video, leave a like, subscribe to the channel, you know the game. All of this helps me so much. And of course, let's talk in the comments. See you in the next video. Bye, my fellow path integrator.